Hello everyone, welcome to the lecture on uncertainty modeling in AI. And today we are going to look at another type of approximate inference algorithm, which is known as the variational inference. Of course, I didn't invent any of today's material. I took most of the content of today's lecture from chapter 10 from the book written by Christopher B. Short. I also took some reference material from the textbook written by Kevin Murphy, David Barber, as well as Daphne Collar. I strongly encourage every one of you to take a look at this reference material after today's lecture. Hopefully, by the end of today's lecture, you'll be able to explain the concept of variational approach using the lower bound as well as the KL divergence. We'll also look at how to make use of the variational approach to do inference on graphical models that contains both hidden random variables as well as the unknown parameters. So in the previous 3 lectures, we have seen that this can be done using the EM algorithm. In particular, we saw that we can make use of the EM algorithm that alternates between the finding of the posterior of the latent random variable as well as the maximization over the unknown parameters. In particular, we look at how to do inference for this particular probability distribution, where theta here is our unknown set of random parameters, as well as z here is our set of latent random variable. In today's lecture, we will see that this can be done concurrently. This means that we will concurrently infer for z and theta without a need for doing the alternating approaches using what we call the variational inference algorithm. So in other words, we are going to look at how to do the inference for this joint distribution here, where z here is going to be a combination. We are going to jointly write both z and theta here as the z in this joint probability distribution over here, where of course x here will still remain as our observed random variable, and we'll see how to do a variational approach over this particular joint probability distribution. Finally, we'll look at how to make use of the loopy belief propagation algorithm to do message passing in graphs, in graphical model that contains a lot of loops. So as mentioned earlier, that the central task of the application of probabilistic model is actually to evaluate the posterior distribution of a set of latent random variable, which we call z here, conditioned upon that we have observed another set of random variables, which we call x. So here z is our latent random variable, and x here is going to be our observed random variable. So in many inference tasks that we have seen over the past lectures, almost the whole semester, we saw that the central task here is that we want to infer the probability distribution given this set of observed random variable over the set of latent random variables. So in the earlier lecture, we call this set of latent random variable our query nodes, and the set of observed random variable as our evidence nodes here. But in this case here, in today's lecture, we're going to simply call this the set of latent random variable, which can also include the unknown parameters of our distribution. So we saw that earlier in the previous 3 lectures, in particular the EM algorithm, the mixture model, and the HMM algorithm, as well as the MCMC sampling algorithm, we saw that we can do this in the alternation of the expectation and the maximization step, where we simply write this this relation over here as x of z conditioned upon theta, where theta here is our unknown random variable and z here is our latent random variable, where we simply evaluate the expectation of the posterior. This means that we do an expectation over this particular posterior of the latent random variable conditioned upon x and theta O, and then we are going to take the expectation of this guy over here over z and log of the complete data likelihood. And we saw that we can alternate between the expectation and maximization step in order to find the unknown parameters as well as the latent random variable. And in the lecture on mixture model as well as hidden Markov model, we saw that the complexity, the computation complexity in evaluating the posterior distribution of P of Z conditional upon X and theta O, it becomes much more complicated as the interaction between the latent random variable increases. And of course, we saw that we mentioned that in the previous lecture on MCMC that if this particular posterior distribution becomes too complicated, we can make use of MCMC sampling to sample from this particular posterior distribution and then directly take the expectation over Z on the complete log likelihood of Pxz conditional upon theta. So this means that we can directly take samples over the expectation step of to find Q, and finally we can do a maximization over the Q on the unknown parameter of the distribution in the EM step. And we also saw that in the mixture model as well as the hidden Markov model lectures that as the interaction between Z gets more complicated, in the case of the mixture model, we saw that all these Z's, they are independent of each other in this plated notation over here. And this leads to a tractable solution when we do expectation maximization algorithm. But in the case of the hidden Markov model, which is a simple link between the consecutive latent random variable, we saw that this particular in this particular case over here, in the hidden Markov chain over here, what happens here is that the evaluation of the posterior distribution of this guy over here becomes much more complicated, where we would need to make use of the forward-backward algorithm or the alpha-beta algorithm in the message passing in order to compute this in analytical form. However, as the interaction between the latent random variable increases, we know that this is not going to be analytically tractable, especially if there are loops in the in this particular interaction between the latent random variable. And we also saw that one particular possibility is to solve this using the MCMC algorithm, but unfortunately the curse of dimensionality means that if the dimensionality of Z is too large, then sampling would become very inefficient. So in today's lecture, we are going to look at how to make use of the variational approach to solve this particular problem in a tractable analytical form. So we also call the variational approach the deterministic approximation or the deterministic approximate inference algorithm in comparison to the stochastic approximate inference algorithm of MCMC, which we have saw in the previous lecture. So this difference here would become very obvious after I talk about the variational inference approach because it doesn't use any random sampling. This means that we don't draw any random number from the random generator in today's lecture of variational approach, and everything would be computed in a deterministic form in an analytical way. And that's why we are calling this particular algorithm the deterministic approximate inference algorithm, and in comparison to the MCMC algorithm, where we saw that we need to draw random numbers, so that's why it's called the stochastic approximate inference algorithm. But in both cases, the MCMC as well as the variational inference approaches, they are both approximate inference algorithm. This is because what we are doing here in the MCMC algorithm is that given a very complicated posterior distribution PZ over X, where we cannot evaluate this or cannot express this in a closed form analytical solution, we draw samples, we draw random samples from under this particular distribution over here. We saw that we can make use of the Metropolis Hastings Gibbs sampling as well as the importance and rejection sampling algorithm to do this task over here. So in other words, this is an approximate inference algorithm because we are drawing samples to represent the closed form analytical solution which we cannot express. And in today's lecture, and we'll see another form over here where similarly we have a posterior distribution PZ conditional upon X which we are unable to express in closed analytical form. So as a result, in today's lecture, we'll look at how to make use of the variational approach where we'll simply express another form which we call a distribution of Q over the latent random variable Z, and we're going to make use of this. We're going to force these two equations over here, these two expressions over here, to be as close to each other as possible. What this means here is that we're going to make use of a analytical form of QZ such that it is able to be as close to, or a very close approximation. For example, this distribution here is going to be as close approximation as to the posterior distribution that we targeted at. And this particular approach here would be known as the variational inference approach. So as mentioned in the previous slide, that the objective of variational inference or the variational approach is that given a joint distribution of P of X and Z, where X here is our observed random variable and Z here is our latent random variable, our goal here is to find the posterior distribution PZ conditional upon X, which is often intractable. So as a result, what we want to do here is that in variational inference is that we want to find an approximation of QZ. This is an approximation distribution QZ which is a function of the latent random variable, to be as close to this particular target distribution of the posterior distribution, which is intractable, as possible. So the key idea here is that we are going to choose an approximation QZ such that the KL divergence between the two distributions, this QZ, which we can also call this our proposal distribution, and this PZ condition upon X, which is our posterior distribution or our target distribution, we want these two distributions to be as close to each other as possible. Hence, this is equivalent to saying that we want to minimize the KL divergence between the two distributions, the proposal and the target distribution, which we simply write it as the KL divergence between Q and P, where Q here is our proposal distribution and P here is simply our target distribution. And this KL divergence we have seen in the previous lecture that it can be expressed in this particular form over here is simply the negative integral of Q log of P of the posterior distribution divided by QZ. And we also saw that this has always got to be more than or equals to 0 according to the definition of the KL divergence. So by minimizing this KL divergence, what it means is that if the KL divergence here between Q and P, the two distribution equals to 0, this is the minimal value that it can attain. What this means is that the Q must be equal to P. We can verify this ourselves by looking at this particular expression over here. In the case where Q here becomes equivalent to P of X, Z condition upon X over here, we saw that this will cancel out, and this term over here would simply becomes log of 1, which is actually equals to 0. And in this case here, the KL divergence would be minimized. So unfortunately, by putting in the posterior distribution of Z condition upon X over here, which is in the first place intractable to compute into the KL divergence expression here, it won't make it easier to compute for the approximate proposal distribution of Q of Z. and this is because in the first place the posterior distribution here is intractable, so computing the whole expression here will still be intractable. So instead of minimizing the KL divergence, which we have seen in the previous slide, we will maximize the lower bound of the log likelihood instead. So the log likelihood or the lower bound of the log likelihood is given by this particular expression over here, and we have seen the derivation of this lower bound and the KL divergence and their relation to the log likelihood in the lecture when we look at the proofs for the EM algorithm. So here's the expression that relates the log likelihood, the lower bound, as well as the KL divergence terms that we have seen or we have proven in the lecture when we talk about the EM algorithm, in particular when we talk about the proof for the EM algorithm. We say that the log likelihood is equals to the lower bound plus the KL divergence term, which can be also described in this particular diagram over here. Here's the log likelihood, and this is a sum of the lower bound plus the KL divergence term, which is always more than or equals to 0. And these two expressions we saw in the lecture of the EM algorithm that after evaluating the sum of these two expressions over here, it will simply becomes the log likelihood. So from this particular diagram over here that depicts the relation of the log likelihood, the lower bound as well as the KL divergence, we can see that if we were to minimize this KL divergence term over here, which is our initial objective in order to make the proposal distribution of Q to be very close to the target distribution of P as possible, and in order to minimize this, we saw that this particular KL divergence term, since it's always more than or equals to 0, it would be minimized when the KL divergence terms tend towards 0. And we can see from this expression over here, or this figure over here, that when the KL divergence reaches 0, this means that the lower bound is being pushed up to this particular term here. And what this means is that by minimizing the KL divergence between Q and P, it's also equivalent to maximizing the lower bound of over the proposal distribution of Q. And the advantage of doing this by maximizing the lower bound instead of the minimizing the KL divergence terms here is that we can see from the expression of the lower bound as well as the KL divergence term from here that what we have mentioned earlier, that the difficulty of evaluating the KL divergence terms is that the posterior distribution of z conditional upon x, which is in the first place intractable to compute, remains in the KL divergence term. But if we were to change it to the lower bound, this means that instead of minimizing over the KL divergence term, we are maximizing over the lower bound, which is equivalent as proven by this particular diagram over here. We can see that now the posterior distribution of z conditional upon x, which is intractable to compute, disappears in the lower bound, and instead we have the joint distribution of x and z, which is what we are given in the first place by the graphical model. So from the graphical model, we can actually get an expression, a closed form expression for this particular joint distribution of x and z. And here, since we are going to do a maximization over Q, we can be guaranteed that this particular expression here is tractable to compute. But now the question is that what would be a good approximation for the distribution of the Q such that we can maximize the lower bound with respect to Q itself. And we'll see in the next few slides that the proof will show us that it's kind of interesting that Q here need not be defined to take any expressions. And what happens here is that by just simply defining the joint distribution from the graphical model, as well as the prior distribution of the unknown parameters and the unknown latent random variables, we'll see that Q here will automatically take an expression that is similar to the conjugate priors of these unknown random variables as well as the unknown parameters through the variational approach inference, where we simply set up to maximize the lower bound. We'll make use of the mean field theory, which is an approximation framework developed in physics to simplify the computation or the maximization of the lower bound. Now, the steps here is that suppose that we partition the elements of the random variables z over here, where take note that in this case over here, z it's containing both our latent random variables as well as our unknown parameters. So now we do not distinguish between these two, where in the previous few lectures we actually distinguish between these two by representing them separately as z and theta. So now we are collectively calling them as together as z. But here in the mean field approximation, we are going to partition these elements of z into disjoint groups, which we denote as zi over here. So here we are going to, what it means is that we are going to partition z into a set of disjoint groups of m, where we have z1 all the way to zm here, where each one of these are disjoint, and each one of these sets over here contains a subset of both the latent random variables as well as the unknown parameters in our graphical model. Following the mean field approximation, we then assume that Q here factorizes with respect to these disjoint groups that we have defined earlier over here, and such that the joint probability distribution of QZ, recall that Z here we partition it into Z1 all the way to Zn, would become a product of the individual factor terms of Qi and Zi, following the mean field approximation theory. We now seek that the distribution of the lower bound is the largest among the distributions, QZ having the form of this guy over here. So what this means is that if we were to look back at this particular expression over here, we are going to maximize the lower bound with respect to Q. And since we have followed the mean field approximation algorithm by simply writing QZ here into the product of the disjoint sets of the each one of these QZIs, what it means is that we are going to plug these particular terms inside here to replace this QZ and QZ over here, such that we'll do the maximization of the lower bound with respect to the individual disjoint distribution over the disjoint groups of the random variables of QZIs. And what's interesting here is that we'll see that since we are doing a maximization over QZI, the respective QZI, on the lower bound, which is a function of Q over here, and since our optimization is done directly on a functional form of Q over here, what it means is that there is no need for us to define the exact form of Q, and the functional or the free-form optimization over the lower bound on Q would end up such that the Q that we are seeking for that maximizes this lower bound to take a functional form of the conjugate priors that we define over the set of random variable zi's. So now let's look at how this maximization over the lower bound with the proposal distribution Q expressed in the factorized form using the mean field approximation theorem. And here we have seen in the previous slide that the target distribution of QZ is now written according to the mean field approximation into the product of the Q functions of the disjoint sets of each random variable denoted as Qi over here. And we are going to plug this into the lower bound expression that we have seen in the previous slide, which we will end up to get this particular expression over here, where simply this product over Qi's over here, it's representing Q of Z according to the mean field approximation theorem, and as well as this is from the denominator that we have saw in the previous slide on the lower bound expression, where this guy over here is also simply the log of the product terms of all the qi's z, which is equals to the log of qz as what we have seen in the original expression of the lower bound. And after we have plugged in this particular equation of following the mean field approximation theorem into the lower bound, we will then split the disjoint sets of this z, the random variable z's, into two sets where we denote as zi as well as the other set which we denote as zj. So what this means is that zj over here represents one of the particular disjoint sets in the mean field approximation of z's that we have seen earlier. So here zj might be any one of these particular disjoint sets of the random variables, and where zi over here would simply represent all the other disjoint sets except for the zj that we have identified from this particular disjoint sets of random variables here. And by splitting z, the random variable, into these two disjoint sets, we can then write the integral form into a double integral over zi as well as zj, and we are going to simply factorize out that particular q, the probability distribution of qj that corresponds to this particular zj that we have defined in the split. And so simply this particular qj will multiply by all the product terms of qi, where I are not equals to j over here, and this term over here is simply q of I, the products of all q of I that we have seen in the earlier expression over here, and we're simply just factorizing out q of j here. So we do this similarly for this particular expression over here to get this expression where we are going to factorize out qj from the rest of the disjoint set of distributions that we define from the mean field approximation. This will allow us to rewrite this expression here into a summation of three double integral terms over zi and zj. In the first term here, this would be simply this term over the integral of zi and zj, as well as the second term here, which is this guy over here, and then the third term over here, which is this guy. We can then see that the expression of the second and the third term can be simplified by pushing in the integral over dz in the second term over here, as well as pushing in the integral of zi in the third term, where both of these terms respectively becomes 1 because we're integrating over qj dj over here, and this means that it is going to sum to 1, as well as we are integrating over zi or over qi, the products of all the qi, where I here not equals to is not equals to j, and the integration of this would also be equals to 1 because we are summing out over all the probabilities in the qi's over here. And this means that we can just simply ignore this term to replace it with 1, as well as ignoring this particular term and replacing it with 1. And what's interesting here is that since our objective is that we want to express the lower bound q over q of j over here, we want to dissect out the dependence on one of the factors of qj, which is our objective here. So what this means is that the second term here, after integrating over zj, which becomes 1 over here, the whole term, we can note that it is independent of zj. It's only dependent on qi, which means that it's dependent on zi's, where all the i's are not equals to j over here. And we can simply treat this particular term here as a constant as a result. So as a result, we are left with these two terms over here, where we can see that the constant term is as a result of the second term, the integration over zj over here, and the second term here it's also a result of the integration, which becomes a simpler form. And we can also rewrite this particular expression, this particular complicated expression over here, into this expression, into a simplified expression of log p tilde x and zj over here. So here we have defined a new expression earlier that this particular guy over here, the log of this p tilde over here, is simply equivalent to this expression, where we can see that this particular expression is nothing but just the expectation over the complete log likelihood of x and z on the expression, on the probability distribution, evaluated on all the joint probability distribution of qi's, where I is not equals to j over here. And we can simply rewrite this expression here into the expectation over the complete log likelihood on the joint distribution of qi's, where I here is simply not equals to j. Here we'll simply shorthand this particular expectation term over here with this expression log of the tilde x and zj that we have defined in the previous slide. Now, substituting this back into the lower bound, which is now a function of qj, we'll see that this particular expression, these two terms over here, it can be merged together since they are both integral over the same random variable or the same set of random variable of zj. We can simply rewrite this subtraction form over here. So qj here we can factorize it out, and the subtraction of log p tilde with log q over here can be rewritten into log p tilde divided by qj here. And what's interesting here is that this particular expression over here, now it's what we are expression that we are familiar with, and this is exactly the KL divergence expression, or the negative KL divergence expression, because qj here and p tilde here are in the opposite direction. So this is the negative KL divergence, where we can simply write this into negative KL of qj and the expression of and the probability distribution of p tilde. And so what's even more interesting here is that since we are maximizing, we are doing a maximization over qj on the lower bound over here, what we can see here is that since this particular term here, there's a negative sign where the KL divergence, we know that it's always going to be more than or equals to 0, which means that when we take the negative sign here, this particular term here is always going to be less than or equals to 0. And if we are going to maximize this term, this negative KL divergence term, plus a constant term which will not affect the optimization, what this means is that we'll simply have to choose a qj such that this negative KL divergence term is equals to 0, which means that this is the maximum value that the lower bound can take. Hence, we maximize this lower bound with respect to qj. And what's interesting here is that we saw that the KL divergence will only be equals to 0, or the KL divergence of two distributions qj and p tilde over here, it will only be equals to 0 when qj is equals to p tilde. So what this means is that we can simply choose the optimal solution of qj to be equals to p tilde x of zj over here. And we know that this particular guy over here, this p tilde of x and zj, is what we define to be the expectation over the log of the complete likelihoods of x and z, which simply means that we can rewrite the log term of this qj here, the optimal qj over here, to be in this particular expression. And what's interesting here is that notice that we have not defined any expression or any distribution for qj explicitly. But what happens here is that the optimal solution for q that will optimize, that will maximize the lower bound, and as a result you will minimize the KL divergence between the two distributions of qz and p of zx, which is what we started off earlier, is in this it naturally manifests itself as a function of the joint distribution, which is given in our graphical model. And we'll see in the later slides on how to compute the optimal Qs for several graphical models examples. But now let's look at the more formal proof on why this particular expression over here is the optimal for the lower bound over Q of J. So we start off from this particular expression, taking the exponential on both sides. We can see that Q optimal J is going to be equals to the exponential of the log of p tilde x zj, which is what we have defined in the earlier derivation, multiplied by the exponential of a constant term, because there's a constant term of addition, and taking the exponential on both sides here. So taking the exponential of this term as well as the exponential of this term here, the sum here naturally becomes a product. And what's interesting here is that we are going to rewrite this particular term over here as 1 over z, where we will define this z over here, this particular z over here. Note that this z here is not the same as the latent random variable of the z in the joint distribution here. Is simply the partition function, where we are going to define it as the integral of the numerator, because we can see that the exponential of the log term over here of p tilde, which is what we have defined, would be equals to simply p tilde x zj and divided by z, which is what we have defined here in this particular case here, and which we are going to further define this particular z over here as our partition function, which we know that this is going to be equals to the integration of the p tilde of x and zj dz over here, such that z is our partition function. Now putting back this qj optima into the lower bound expression which we have derived in the previous slide, we can see that now we reach this particular term of the negative KL divergence of p tilde x zj divided by the partition function and over the p tilde expression plus a constant. And we can see that we know that the KL divergence, the negative KL divergence, is always going to be lesser than or equals to 0, and it becomes 0 when this lower bound is optimal. So from the proof, we can see that the full expression for the optimal expression of qj that maximizes the lower bound of qj can be obtained, can be rewritten into this particular expression over here, where we saw that the this qj optima is simply equals to p tilde of x zj divided by the normalization or the integral over p tilde x zj dzj over here, where this particular term here is simply equivalent to what we have defined earlier on the exponential of the expectation on the log joint probability distribution of x and z. And we'll do simply do the partition function over here. This guy here is our partition function by integrating it over z of j. Now it's important to note that the KL divergence is not symmetrical. Minimizing the KL divergence of Q and P is not the same as minimizing the KL divergence of P and Q, and they both will give different results. We'll see an example here to illustrate that the difference between these two KL divergence. The KL divergence of Q and P is equivalent to this expression over here, where we see that it's QZ log of P over Q, where in the case where this is continuous, Z is continuous, we'll simply replace the summation with integration over D of Z over here. And we can see that the KL divergence of PQ is different, where we will need to flip the P and Q around in this particular case here. So in this particular example, let's look at the case where the probability distribution of P is equivalent to a Gaussian distribution or normal distribution of zero mean as a standard deviation or variance of sigma square, as well as we'll define the probability distribution of Q to be a normal distribution at the mean of 2 and a standard deviation of sigma 3. You can see that the distribution looks like this, the red curve as well as the blue curve over here. And we'll plot a computation of these particular terms, these two terms over here, where we can see that the red curve over here simply represents the probability or the distribution of this expression over here, q log of p divided by q over here. And for the blue curve, it's it's the other way around, where we simply plot the negative of the p log of q divided by p over here. And we can see that the distribution here, the two functions here, the two curves here, they already look dissimilar. And we'll finalize this by computing the KL divergence as the area under this curve, because the KL divergence is simply, in this case here, x is, or z here is a continuous random variable. This means that we need to integrate this over dz to get the KL divergence, as well as integrating this over dz. So we can see from this plot over here, the area under these two curves, where one of them represents the blue curve over here represents the KL divergence of PQ, and the red curve over here represents the KL divergence of QP. We can see that the area under these two curves, they are not the same, and hence we can conclude that the KL divergence is not symmetrical. Thus, we need to in our minimization or in our optimization of this particular KL divergence terms in the derivation of the variational inference, we need to choose a particular setting of QP or PQ. And we first, let us consider the reverse or the backward KL divergence of QP over here. This is just a terminology that represents this particular KL divergence expression, or it's also otherwise known as the I projection or the information projection. We saw in the previous slide that this KL divergence here can be written as this expression over here. In fact, it should be written as the negative of the summation of z qz log of pz divided by qz. But if we were to flip these two around, then the negative sign will be absorbed. So, and in the end, we'll end up with this particular expression over here. And what's interesting with this particular expression is that we see that it will become infinite if pz equals to 0, because we'll be dividing something with 0, and qz is more than 0. Thus, in order to avoid this kind of situation, if pz is equals to 0, in order to avoid this term here from becoming infinity, from tending towards infinity, what we need to ensure is that qz must also be equals to 0. Hence, we say that the reverse KL divergence is 0 forcing for q, which is our proposal distribution. This means that in the regions where the target distribution is 0 or is taking a very low value, the ending results of minimizing these terms will be that the proposal distribution will also be similarly low value, or it must also be 10 to 0. Hence, the term of 0 forcing for q. We'll also see an example that this will typically underestimate the support of the target distribution. Next, let's look at the forward KL divergence, or otherwise known as the M projection or moment projection, and it's defined in this way that we are taking the KL divergence of P and with respect to Q over here, and this is equals to the by right, this is supposed to be equals to this guy over here, P of Z log of Q Z and P of Z, but there's a negative sign here. But if we flip these two around, then the negative sign gets absorbed into the summation term, and as a result we get this expression over here. And what's interesting here is that we can see from this particular expression over here that it becomes infinite when q equals to 0 and p is more than 0, and thus if p is more than 0, we must ensure that this particular guy over here, Q, must also be more than 0 in order for this whole term here, in order for it not to become infinity. So we typically say that this forward KL divergence is 0 avoiding for Q. Hence, as a result, Q will typically overestimate the support of P. What this means is that for the regions where the probability distribution of P, Z, which is our target distribution, is more than 0, then as a result of this forward KL divergence, minimizing this forward KL divergence, we will end up with the proposal distribution of QZ which is going to be also more than 0 in the region where the target distribution is more than 0. Hence the term 0 avoiding, and we will see an example that this is going to typically overestimate for the support of P. Here's the example where the target distribution is given by the blue curves over here. So this is our P of Z, and we can see that minimizing the forward KL divergence PQ here, where this red curves over here is our Q of Z over here. Since it's 0 avoiding, what this means is that when the target distribution, the blue curves over here, in the region where it's going to be non-zero, all these regions over here where they are non-zero, we can see that the proposal distribution must also be non-zero. And in the case of the backward KL divergence, which is defined by the KL divergence of Q on P, we can see that in this case here, if we have the blue curves as our target distribution P of Z, since it's 0 forcing, this means that in the region where the target distribution is very low, we can see that in this region over here is very low, then we should also have QZ, our target distribution, to take a low value because it's 0 forcing, in order to prevent the case where the KL divergence becomes infinity. So as a result, we can see that these regions here, which corresponds to the unimodal Gaussian distribution over here that represents QZ, must fit into a region where it takes concurrent low value when the target distribution is also low value. And in this case here, since we are using a unimodal distribution of Q to approximate the bimodal distribution of P, the target distribution, we will end up to have two solutions where it could be 0 forcing. In the first case here is that the optimal, the peak will align with the first peak in the target distribution. It's 0 forcing. We can see that the low values of this Q corresponds to the low value of P, as well as in the second case here where the blue curve here is also PZ, and the red curves over here, it's representing our proposal distribution of QZ. We can see that it's 0 forcing because in the region where Q is small, P is also going to be small. Now, comparing the two, the forward and the backward KL divergence, the 0 forcing as well as the 0 avoiding, we can see that in the case where in the backward KL divergence, which is 0 forcing, will tend to underestimate. This is because in this example here, where the green curves here is our target distribution and the red curves here is our proposal distribution of Q, in order for it to be 0 forcing, this means that in the region where P is taking a very small value, then Q should also subsequently take a very small value. We can see that because of this axis over here, P will take a very low value very quickly, and in order for Q to approximate or to be 0 forcing, then we can see that Q here is going to underestimate because all these regions over here are not going to be represented well. But in the case where it's 0 avoiding, this means that we are reversing P and Q. We can see that since it's 0 avoiding, this means that we want to make sure that Q takes a large value, or Q should be more than 0 when P of Z is equals to 0. And in this particular case over here, we can see that it becomes overestimation of this target distribution, because in order for these conditions to happen, when PZ becomes 0, very small values, QZ has to also have a sufficient coverage in order to ensure that it's more than 0 for it to be 0 avoiding. So we've seen the difference between the forward and the backward KL divergence, and now the question is that which one should we use for our variational inference? And the choice is that we will use the backward KL divergence, which is given by this expression over here, because it leads to a tractable lower bound equation or expression, or as shown in the previous slide, or as shown in this particular expression here. The reason is because in this case here, we see that Q is our proposal distribution, and our target distribution here is the joint distribution between X and Z, where this is directly given by our graphical model. And we saw that in the earlier slides, in the derivation of our variational inference, that this leads to a tractable optimal solution when we optimize over the lower bound. And let's compare this to the forward KL divergence, which is given by this particular expression over here, and we can see that it actually leads to a intractable lower bound, where the lower bound in this case here, using the forward KL divergence, will be given by this expression here. And what happens here is that since we swap the position of P and Q in the forward KL divergence, will lead to a lower bound where we still have the joint distribution of X and Z, but now instead of Q, we end up to have the posterior of Z conditioned upon X in both locations over here. And we know that this is our objective, that we want to do variational inference, which we want to approximate this intractable term here with our proposal distribution of QZ. But in this case here, having this particular expression, this particular intractable expression appearing in our lower bound, it means that it's no longer tractable to optimize our lower bound term here. Another reason why we choose the backward KL divergence is because it's statistically more sensible compared to the forward divergence, the forward KL divergence. And because we have seen in the previous example here that in this case here, we are minimizing the forward KL divergence terms, which is given by this expression over here. We saw that in comparison with minimizing the backward KL divergence in this solution over here, these two examples over here, where we try to approximate the target distribution, which is a bimodal normal distribution or mixture of Gaussian distribution given by PZ over here. We see that there are two peaks over here with a proposal distribution or a unimodal proposal distribution QZ, as shown by this red curve over here. We can see that in these two cases here, because the backward KL divergence is zero forcing, as a result we can see that it is able to approximate the bimodal distribution better, because the peak will be aligned in this particular case here, despite that there could be two possible solutions here. And in the zero avoiding case over here, where we optimize over the forward KL divergence, we can see that this is statistically less sensible, because what happens here is that the peak of our proposal distribution QZ, it's right at the valley of this bimodal target distribution that we wish to approximate. Hence, our choice would be simply to use the backward KL divergence in the variational inference approach.